In this video, we're going to talk about adding and subtracting vectors in R2 and R3. Any vector in the two-dimensional plane can be expressed in terms of the unit vectors I and j, where I is equal to the vector 1, 0, and j is equal to the vector 0, 1. So for example, the vector negative 3, 4 can be thought of as negative 3 times 1, 0 plus 4 times 0, 1, or in other words, negative 3i plus 4j. This is the sort of thing that most students will just do by recognition without much thought when they get used to vectors. Negative 3, 4 will be negative 3i plus 4j. And it also works in three dimensions. Instead of I being 1, 0, because we're in three dimensions, I will be the vector 1, 0, 0, j will be the vector 0, 1, 0, and k will be the vector 0, 0, 1. And then ultimately 5, negative 2, negative 3 will equal 5i minus 2j minus 3k. Now, as a general rule, the distributive property works in the following sense. If I have a vector v, which is equal to ab, then kv, in other words, k times the vector ab, will be equal to the vector ka, kb. So for instance, 5 times the vector 2, negative 3 will equal the vector 10, negative 15. You just distribute in that 5 to each of the two components. Very, very user-friendly. And it works in three dimensions as well. So if I want to multiply negative 4 times a particular three-dimensional vector, I can just multiply each of those components by negative 4. Very user-friendly. Now, what if we are adding and subtracting vectors, as shown here? Well, suppose we have the vector A, which is 1, 3. That represents a journey of 1 unit to the right and 3 units up. 1 unit to the right and 3 units up. And similarly, the vector 4, negative 2 represents a journey of 4 units to the right and 2 units down. Well, if I want to add those vectors, then what I'm going to do is do my start at the origin, do my journey of 1 unit to the right, 3 units up, and then do my journey of 4 units to the right, 2 units down, and find out what the resulting journey is, that this boldest of the three vectors shown. Well, if you just count squares, you'll see that you end up at the point 5, 1. But perhaps you want a slightly quicker method than having to graph every time and count the squares. And there is such a quicker method, actually. What we can do instead is just add the x components of the two vectors. So if I'm adding vector 1, 3 and vector 4, negative 2, 1 plus 4 is 5. And 3 plus negative 2 is 1. I end up essentially doing the resultant vector 5, 1. Add the x components and the y components. So in short, in two dimensions, if A is x1, y1 and B is x2, y2, and those are vectors, then A plus B will be x1 plus x2 and y1 plus y2. And it will work just as well in three dimensions. A plus B will be the vector x1 plus x2, y1 plus y2, z1 plus z2. Now, what if we're subtracting b from a? That's like asking what is the vector a minus the vector b equal? Well, that's the same as asking what does a plus the vector negative b equal? And so we're just adding the opposite of vector b to the vector a. So in the situation we just had, the vector a is 1 unit to the right, 3 units up. The vector b, if you recall, was 4 units to the right and 2 units down. So the opposite of that will be 4 units to the left and 2 units up. And we'll end up with the resultant vector shown. Well, rather than having to count squares, as we said, it would be good if there was a more convenient way just looking at the numbers. And perhaps it's no surprise to you that there is such an easier way of doing it. The net effect is, like it says there, move 3 units to the left and 5 units up. But what we can do is simply determine 1 minus 4, which will be negative 3, and then determine 3 minus negative 2, which will be positive 5. We simply subtract the components in the similar way that we added the components. So if A is the vector x1, y1, and B is the vector x2, y2, then A minus B will be the vector x1 minus x2, comma, y1 minus y2. And the analogous thing works in 3 dimensions as well. Now, what if we're going from one point to another? If we're going from one point to another, then we have formulas as shown. I'm going to jump forward a few slides and show you something kind of cool. Suppose we started at the point -1, 3 and we ended at the point 4, 2. So what I'd like to know is what vector have we just drawn? Well, if we counted squares, we'd see that we've gone 5 units to the right and we've gone 1 unit down. So we would say that to go from point A to point B was equivalent to a journey of 5 units to the right and 1 unit down. Rather than having to count squares, though, we can do something really ingenious. We can just look at the x-coordinate of point B, which is 4, and subtract the x-coordinate of point A, which is -1. And we can look at the y-coordinate of point B and subtract the y-coordinate of point A. We'll get 2 minus 3. And so that is the quicker way to determine the vector AB, is just to subtract backwards, okay, as shown here. So we would say that given these 2 points, the position vector, in other words, the vector between them, would be determined just by subtracting backwards, as you might say in slang. 4 minus -1 and 2 minus 3. Okay? Now, that brings us to the formulas shown here. If you're going from point A to point B, then take B's x-coordinate, subtract A's x-coordinate, and that'll be the x component of your vector. And then take B's y-coordinate, subtract A's y-coordinate, that'll be the y-coordinate of your vector. Well, a similar process works in 3 dimensions as well. Okay? But now, how do we determine the magnitude? Well, let's just skip forward a couple of slides here and just take a look. Basically, what we're saying is, what is the magnitude? If we're asking what is the magnitude of AB, the vector, we're asking what is the length of that diagonal? Well, we're basically just saying what is the magnitude of that side squared, and then adding the magnitude of that side squared. Now, since we're squaring it, we can actually keep it negative. The y component there of the resultant vector is -1, but 1 squared is the same as -1 squared. So we can actually say, using the Pythagorean theorem, that the hypotenuse squared will be equal to 5 squared plus -1 squared, or in other words, the hypotenuse will equal the square root of that, or in other words, the magnitude of AB will equal the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay, so moving backwards, that's what we get. The magnitude of AB is actually equal to the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And in 3 dimensions, the same process works. It's the sum of the squares of all 3 components, square rooted. So to put that into practice, what if we had a question like this one here, where we're in 3 dimensions, and we say the point A is the point 3, 2, -5, and point B is the point -4, 0, -3. We want to know what are the components of vector AB. So we'll just subtract backwards. -4 minus 3 will be -7. And then we'll, again, since we're going from A to B, we'll subtract those coordinates backwards. The y-coordinate minus the y-coordinate will be 0 minus 2, which is -2. And then, of course, subtract the z-coordinates backwards. -3 minus -5 will be +2. And so the z component of the resultant vector AB will be 2. So the vector AB will be equal to the vector -7, -2, 2. To determine the magnitude of vector AB, we'll simply add the squares and then square root the result. It's like a three-dimensional Pythagorean theorem, and we get root 57 as our final answer. Now suppose we're given a parallelogram OABC, and we see that we've got the vectors OA and OC. And we want to determine what the vector OB looks like, as well as the vector AB and the vector BC. Well, what we can do here is begin by drawing as much as we know. O is always going to be the point 0, 0 by default, or in 3 dimensions, 0, 0, 0. So we draw the vector OA and we draw the vector OC. Now, if we're considering the parallelogram OABC, we have to go in order from O to A to B to C. So B, just by instinct, is going to be somewhere out in this part of the graph, and then back to C. So it's going to be O, A, B, C. Well, what we're looking for right now are the coordinates of point B. Okay. So B is going to be out here somewhere. Now that's going to be the point XY. Well, think about what we just said a minute ago. We know that the vector AB will be equal to the x coordinate of B minus the x coordinate of A, so x minus 7, and then the y coordinate of B minus the y coordinate of A, so it'll be y minus 4. So the vector AB will be equal to x minus 7, y minus 4. But since it's parallel, that'll be equal to the vector from 0, 0 to 1, negative 6. Well, the vector that goes from 0, 0 to 1, negative 6 will be equal to the vector 1, negative 6. So, in other words, we're saying x minus 7, y minus 4 must equal 1, negative 6. And from there, it's going to be pretty easy for us to determine what our x and y values are. So just to show it perhaps a little bit more neatly, we're going to see that the vector, this is what it says here, the vector AB must be equal to the vector OC. Well, we know AB, as mentioned earlier, will be x minus 7, y minus 4. But we already know OC is the vector 1, negative 6. That's this one here. So that means that x minus 7 will equal 1 and y minus 4 will equal negative 6. That means x will equal 8 and y will equal negative 2. So we can change our diagram like that. And so now it asks us, what is the vector AB equal to? Well, in a sense, we already knew what the vector AB equaled. AB equaled 1, negative 6. But just to show that, AB will be B's x coordinate minus A's x coordinate. 8 minus 7 will be 1. And it'll be B's y coordinate minus A's y coordinate. Negative 2 minus 4 will be negative 6. Okay, so AB will be 1, negative 6. And the question also wanted to know what BC was equal to. Well, BC is backwards. Well, we know OA is 7, negative 4. Since BC is parallel but in the opposite direction, BC will have to be negative 7, negative 4. We know that just by observation, but if instead of just doing it by observation, if we wanted to show our evaluations, we could say BC was equal to C's x coordinate minus B's x coordinate. 1 minus 8 is negative 7, and C's y coordinate minus A's y minus B's y coordinate. Negative 6 minus negative 2 is negative 4. Now, in this question, we want to find the components of a unit vector in a direction opposite to CD, where OC is the vector negative 3, negative 6, and OD is the vector negative 11, 9. So we draw our diagram here. Okay, OC and OD are as shown. Pretty easy when it's in 2 dimensions. Now, the direction opposite to CD will be the same as the direction DC. So we're going to draw in the vector DC, and we're going to determine the vector represented by DC. Well, DC will just be -3 minus -11, which is 8, comma, -6 minus 9, which is -15. Now, we want to get a unit vector in the same direction as 8, -15. The way we do that is we're going to determine what is the magnitude of the vector 8, -15. It's going to turn out that the magnitude of 8, -15, just using the Pythagorean theorem, is 17. We have a 17 unit long vector. We only want it to be 1 unit long, so we're simply going to multiply the vector by 1/17. That way it'll make it 1 unit long. Well, the more general way of saying that is to get a unit vector in the direction that we want it to be, what we're going to do is multiply the vector that the correct direction, in this case the 8, -15, multiply it by 1 over its own magnitude, which in this case is 1 over 17. So let's see that work. We see that DC is right here. DC equals the vector 8, -15. 8, -15. And what we're going to do is determine the magnitude of 8, -15 and multiply the vector 8, -15 by 1 over that magnitude. So the magnitude of 8, -15 is given by the square root of 8 squared plus -15 quantity squared, which ultimately equals 17, telling us that 8, -15 is 17 units long. So multiplying that vector by 1 over 17 maintains the same direction, but makes the vector resulting in the direction that we like it to be only 1 unit long. In other words, a unit vector in the direction that we want it to be. So we can say the unit vector in the direction opposite to CD, which is the same as DC, can be expressed as 1 over 17 times the vector DC, or if you prefer, you can call it 8/17, comma, -15/17. And now, finally, we know that DC is the vector 8, -15. That's one side of the triangle. OD is the vector -11, 9. That's another side of the triangle. And OC is the vector -3, -6. That's another side of the triangle. If we want to know the angle between OC and OD, which is given by theta in my diagram, all we have to do is figure out the magnitudes of these three vectors, and then that'll give us the side lengths of the triangle, and then we can use the cosine law. So we see that vector DC, as stated earlier, is 17 units long. Vector OD is root 202 units long, and vector OC is 3 root 5 units long. And using the cos law, we can see that our angle theta can be determined as shown. Anytime you have side, side, side of a triangle, you can use that method shown. And ultimately, we get theta is roughly equal to 102.7. So since the vectors are tail to tail as drawn, we can see the angle between OC and OD is approximately 102.7 degrees. Now, if u is equal to -2i plus 9j plus 6k and v is equal to I minus j plus k, we want to determine the vector 3u minus 2v and the magnitude of the vector 3u minus 2v. Well, this question is more just an algebraic exercise for you to get used to seeing that the distributive property works really nicely in these circumstances. U is the same as -2u plus 9j plus 6k, and v is the same as I minus j plus k. So we distribute in this 3, and we distribute in this -2. And when we do all that, and we collect like terms, we ultimately get that 3u minus 2v is equal to negative 8i plus 29j plus 16k. Well, if we want to determine the magnitude of that vector, the magnitude of that vector will be the square root of 64 plus 841 plus 256. And there's a little typo. That's actually the square root of 1,161, not 1,181. Now, imagine we have a parallelepiped formed by the vectors OA, OB, and OC. We want to determine the coordinates of all the vertices for the parallelepiped. Well, a parallelepiped is a solid body of which each face is a parallelogram. The simplest example of that would be a cube or some other rectangular prism. Now, we can draw a diagram, but thankfully it's not going to have to be to scale. We can just draw a cube, and the principles will help us to get through the question. It's similar to if you're doing a trigonometry question. You don't actually have to draw your triangle to scale. You can just make the simplest triangle you want, put the measurements in, use your trigonometry, and you'll get the right answer. Similar concept to here. We don't actually have to try to draw our parallelepiped to scale. Instead, we can just simply draw a cube as we do here. We're going to pick one of those corners to be the point 0, 0, 0. And then the three edges emanating off of 0, 0, 0 will be the three vectors shown, 3, negative 1, 4, 1, negative 1, 8, negative 7, and 4, 0, 9. And from here, the question actually is pretty straightforward. We just want to label the four remaining vertices, and we're going to let G have the coordinates G1, G2, G3. And if we do that, we can see that this vector, which is 4, 0, 9, will have to equal this vector. So the vector from A to G will have to be 4, 0, 9. Sorry, 4, 0, negative 9, which means G1 minus 3 will have to equal 4. G2 minus negative 1 will have to equal 0, and G2 minus 4 will have to equal negative 9. And when we set that up, we get that G1 will have to equal 7, G2 will have to equal negative 1, and G3 will have to equal negative 5. So the coordinates of point G will be 7, negative 1, 5. Now you might be curious, how did we know to go this way and compare it to this side rather than going this way and comparing it to this vector over here? And the answer is we would have got the same answer no matter what. That's what's pretty cool about a parallelepiped. So we'll add those coordinates in. And so now let's think of F as having the coordinates F1, F2, F3. And if we do that, then we see that 1, 8, negative 7, which is OB, will have to be equal to CF. So F1 minus 4 will have to equal negative 1, and F2 minus 0 will have to equal 8, and F3 minus negative 9 will have to equal negative 17. Putting all that thinking together, we see F1, F2, F3 will ultimately be 3, 8, negative 16. We'll add those coordinates in. And from here, the question is pretty similar for the rest of it. We are going to look at point D, and we're going to see that the vector from B to D will have to be equal to the vector from O to A. So the vector from B to D will have to equal 3, negative 1, 4. And doing some simple solving, we get that the coordinates of point D will be 2, 7, negative 3. And finally, the coordinates of point E, I should say at the bottom here, will be 6, 7, negative 12. Okay. And so we get those coordinates of those points labeled pretty nicely. And then finally, we want to determine the midpoint of two points. And the formula here is analogous to the one that you learned probably in about grade 10 for the midpoint between 2 points in 2 dimensions. We're simply going to add the x components and divide by 2, add the y coordinates, sorry, I should have said coordinates instead of components, and we'll divide by 2, and then add the z coordinates and divide by 2. And when you do that, we'll see that the midpoint is -1, -4, 8.